Good morning, guys. Today we're going to expand on that last lecture we did where we worked with quantitative data, but we looked at it graphically. Today we're going to do some summarizing, but we're going to do it calculation-wise. So we're going to take a quantitative data set and we're going to get it into what we call summary statistics. Single values that kind of give us an idea of what's going on with the distribution. So set up for today. Number of home runs Hank Aaron hit in each of his 23 seasons playing Major League Baseball are listed here. Went ahead and ordered them from least to greatest. Again, with quantitative data, it makes sense to put them in order, put them like on a number line. So out of all those, we can see his worst season was at 10 home runs. His best season was at 47 home runs. So we want to get an idea of kind of what kind of home run hitter was Hank Aaron. So first thing we want to talk about is measure of center. Measure of center, if you remember in the last lecture we did, is kind of your one number best guess. So I like to think of measure of center as the typical value. Okay? The typical value of a data set. So when I say typically, how many home runs did he have? Or what type of home run hitter was he? You could say, on average he hit this, or his median value was this. So we kind of have this one number that summarizes what we would expect from him from one random season or something close to it. So the typical value of the data set. Now, I've already mentioned one of them, really two of them. When we're talking about measures of center, things that are going on towards the middle of a distribution, these are things you've worked with before. And we have two of them, the median and the mean. Now, you know of the median as the middle number, right? So that's all it is. It's the middle value of an ordered data set. The middle value of an ordered data set. So we put numbers in order, we find out which one's in the middle. Obviously, that would be the center of that distribution. So if we look at this one, we've got all these values here. There were 23 of them, so we can kind of reason through. For 23, that puts 11 in the first half, 11 in the bottom half. So the 12th number, counting 11 from each side, would give us our median. But we're going to come back to using a calculator to get that. But that's the idea behind the median. All right. The other one that we talk about often is the one that probably most people use, sometimes correctly, sometimes incorrectly, is the mean. Okay. Mean is nothing more than an average of all values in the data set. So y'all know average. You take all the values, the entire list of numbers, add them all up and divide by however many there were. So that's what I mean by the average of the data set. So let's step over to the calculator for a minute and we'll look at how we can use some of our calculator features to be able to get the mean and the median. So here we have the calculator. First thing we need to do is get the data set keyed into the calculator. Where we're going to do that is in the Stat menu, so hit your Stat button right here. Then we're going to go to hit Enter for Edit. In L1, List 1, we're going to key these values. They don't have to be in order. The calculator can reorder them as it needs. So we just need to key each of these values in. And just kind of double check as you go to make sure you don't have any errors, because obviously if a number is off, then the calculations you do are going to be off. So just kind of carefully check as you go. Quick scan up. Looks pretty good. Okay. So now we can see we've got all of our values keyed in. Now we're ready to do calculations. So we're going to hit Stat, Calc. So hit the over arrow, get into the Calc menu, and we want one var stats. That's option 1. So our data is in list 1, so L1, we're good there. Don't worry about frequency lists. That's something that we'll use later. We don't need it in this situation since we keyed in each number. And then we go to calculate. You can see a lot of numbers are generated here. If you scroll down, You see MED, that's median, 34, which we can see right over here is in the middle because we had 11 numbers before the 34 and 11 numbers after the 34. Now the other one we're interested in is this one right here, that X with a line above it, that's called X bar, 32.826, that is our mean. So X bar is our symbol for mean, so that's 32.83 home runs a season is what he averaged. All right, let's take a look at how we can use each of these numbers. Now, as we just saw on the calculator, MED from when we run our one bar stats is going to give us the median, that's 34, and X bar, that's what we're going to call this guy right here, X with a line over it, we call him X bar, that's his name. He's going to give us the mean of the distribution. So we can see median is 34. So just like if we had counted it out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, the 12th term should be our median. If we're dealing with 23 numbers, because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 on below it. So that was our median. All right, so we can get it just by counting and finding the middle value. Remember, you can average them if it's an even number of terms. Or we can use the one var stat. I like one var stats just because it gets us in the habit of doing all of those things. And then the mean, which is the X bar, the 32.83. Now, when you have, well, let's talk notation real quick. This X bar that we have here is actually the notation for what we call sample mean. So if we don't have all of the data from a population, we just have the data from a portion of the population, maybe a subgroup, a sample of the population, then we would use X bar to represent that. It just kind of lets someone who's reading your work know, okay, this was calculated from a sample, not from a whole population. If we did have the population, which is what we have here, all of the seasons that he played, then we wouldn't actually use X bar. We would use this Greek symbol right here. Okay. That is known as mu or mu, just depending on who taught you how to say it. Mu or mu. It looks kind of like a U or an M, but that's the Greek lowercase mu, mu for mean. So if we're talking about a population, we're going to use this symbol. Again, it lets people know where you got your information from. If you're talking about only a sample, you're going to use X bar. The calculator only does the X bar because they're calculated the exact same way. So this is if we have population mean. Median, it's just median. We don't care how it was calculated. Okay? Or we care how it was calculated. We don't care whether it came from a sample or population. All right, now you have two centers here. How is that possible? How can we have two things that measure the center, especially in this case when they end up different? So what I want to do is I want to take a second and I want us to sketch the histogram, just like we did in the last section, histogram of this distribution so that we can figure out which one of these values. Remember we talked about the center is your one number best guess. Which one of these values is truly the most representative of this data set? So let's take a second and let's sketch this histogram, this stuff as a histogram. So I've got 10 to 15, so that's 1, 2, 3 values. 15 to 20, I had no values. 20 to 25. 45 to 50, we had 2 seasons. Okay, so if we make some observations about this group right here, shape on this, I feel is pretty obvious. It's a left skew distribution. Most of our data is clumped here and then it tails off to the left. So I think we could safely describe this distribution as being left skew. All right, so let's mark our mean and our median and try to figure out which one's a better approximation. So our median was at 34, right about there. Our mean was at 32.83. All right, so you can see those two values pretty close together, both towards the center, but how do I decide which one to use? So was he a 33 a season hitter, or was 34 a better estimate of what he would hit? Well, the way we decide this is based on the shape. This is why we talk about when we're describing the socks, shape is the first thing we identify, because shape is going to dictate how we summarize, which summary statistics we use. So if we think about when's median appropriate, when's mean appropriate, we need to follow these two rules right here. We need to remember that median is resistant, keyword there, resistant to extreme values. The median is resistant to extreme values. Well, what do I mean by resistant? Resistant means that if a value changes, then the measure does not change. Okay, so let's say that instead of hitting 47 home runs as his highest season, he had hit 75 home runs in that highest season. So that 47 just becomes a 75 or a 74, so you wanted to flip it. So if that was a 74, does it change what the middle number is? No, 34 is still going to be the middle value. This part of the graph is just going to move out here. There's just going to be a little peak out here, or a little value out here. So resistant means if I changed a value, an extreme value, see, resistant to extreme values, the median's not going to change. Now, if I took that 47 and changed it to a 74, would the average change? Would the mean change? Well, I think it's obvious that it would, because remember, a mean is just a sum. You're adding all the values together. Well, if I'm adding a bigger number in, so look, the 47 changed to 74, I now have, what's that, 27 more points, or 27 more home runs to get to average out and distribute across all those seasons. So because I'm adding a bigger value, and mean is just a manipulation of the sum of the values, then that means my mean would actually increase in this case. So what we say is that mean is not resistant to extreme values. Not resistant. And this idea right here is what dictates for us whether we're going to use mean or median based on the shape. So what we can see is, since mean gets kind of pulled towards the tails, right, those extreme values show up. So if I had a bigger value out here, the mean would get pulled in that direction. Well, see how we're a left skew and the mean is further to the left? So we notice that mean gets pulled towards the tail. So if we have a symmetric distribution, the tails are even. So my mean is going to be sitting right in the center of the distribution. But if I have a left skewed distribution, tail on the left, then the mean is going to be a little bit further left, like we have here. If I have a right skewed distribution, then the mean is going to be a little bit further right, like I do here. Where median's always in the middle. It's by definition the middle number. So it doesn't matter what the tails are, median is always going to sit in the middle of the distribution. So when trying to decide, am I going to use mean or median, what my appropriate measure of center is, if it's symmetric, we're going to go with mean. The reason we like mean is because mean brings all of them. It's kind of democracy. Everybody gets their vote in there. So we like to use mean anytime we can, but we can really only use it if it's symmetric, because it's not representative of the center if you have a skewed distribution. So for a symmetric distribution, that's when we get to use mean. And for a skewed distribution, if we want really what's going on in the center of the distribution, then we need to be using median. For skewed distributions, it's median. So in this case, if we want to say what's the typical number of home runs that he hits in a season, I would say his median number of home runs is 34. That's the way I would answer that question. So in this problem, median was the appropriate center. Median was the appropriate center because it's a skewed distribution. Our mean is no longer in the center, our median still is. All right, next let's talk about measures of spread. And we've talked a little bit before when we were looking at shape, outlier, center spread, describing the distribution. So in those situations, measure of spread is nothing more than a measure of the variability. A measure of the variability of a data set. So it's just telling us, giving us an idea, are they really close together? Are they really spread out? Is it really wide? Are there kind of gaps and things like that? That's what I mean by variability. How consistent was this data? Okay. So we talked about the big spread, things like range, maximum minus minimum, the width of that data set. So if we did this one, the range of his data, of his number of home runs in this case. So if we came back over and let's fix that 74 and put it back at a 47 home runs. So if I did my maximum minus my minimum, maximum. So in this, we can see that he hit 47 home runs maximum, 10 home runs minimum, so 37 home runs. That's his range. So the number of home runs that he hit in a season varied by 37 home runs. Okay? So that's how that works. That's the variability of it. Now, interquartile range and standard deviation get us into this internal spread that we talked about. What's the space between individual seasons? Not the overall span, but just between those individual seasons. So interquartile range is exactly what it sounds like. Interquartile. Inter means between quartiles. Well, what's a quartile? So on my interquartile range, let's say that we have our data set and it's just a bunch of numbers. I put them out in a line. Okay. And then I wanted to divide it into 4 equal parts. Okay, so each chunk here represents 25% of the data set. So, for example, this one right here, maybe this is like 6 values, 6 values, 6 values, 6 values. So we put the numbers in order and then just divide it into 4 parts. Well, you know that the middlemost part is your median, like we talked about. Well, this first part is what's known as Q1, or the first quartile. It denotes the first quarter of the data. This third one down here, that's Q3, or your third quartile. It denotes the 3/4 mark of the data. So what we've done is these quartiles break our data into 25% chunks. So when we're looking at interquartile range here, we're actually looking at the width of the middle 50% of the data. The width of the middle 50% of the data. Well, why do we care about the middle 50%? Well, we mentioned before, the middle, the center is typical. So while we said the overall distribution varied by 37 home runs, you can say his typical seasons varied by this many home runs, whatever the interquartile range happens to be. All right. So how do we get interquartile range? Well, it's a range. Range is just maximum minus minimum. So it's maximum quartile minus minimum quartile. So your interquartile range is nothing. When we abbreviate that with IQR, then taking your maximum quartile, Q3, and subtracting your minimum quartile, Q1. Now, if we jump back over to the calculator, let's look and see how we can get that Q3 and the Q1 so we can figure out the interquartile range. So back here in one of our stats, in the exact same program we used before, we're just looking through this list of numbers. Down here at the bottom where we found the median, you'll see it listed Q3 and Q1. So our Q3, our third quartile, is 44, and our Q1, our first quartile, is 26. All right, so as we saw on the calculator, the Q1, when we did that 5-number summary down at the bottom, the Q1 was 26. Q1. And then our Q3 was 44. Well, I got a lot of 44s on here. Well, think about what we're doing here. I'm trying to break into equal parts in this case. So in front of my Q1, say I'll have 1, 2, 3, 4, 5 values. After my Q1, 1, 2, 3, 4, 5 values. After my median, I should have 1, 2, 3, 4, 5 values. Then we should have our Q3. So that's why 44 is the Q3. That's how it came up with that number. So then we have 1, 2, 3, 4, 5 values after that. So we've taken our data set of 23 seasons and we've turned that into 4 chunks of 5 seasons split up by the median and the Q1, Q3. Median is technically your Q2. So if you ever see a question on Q2, it's really just talking about the median. So our Q1 and Q3 are just going to end up being 44 home runs minus 26 home runs. So our interquartile range becomes 18 home runs. So while his overall number of seasons varied by 37 home runs, his typical number of seasons varied by only 18 home runs. So he got a lot more consistent in that typical, which that should kind of make sense. All right, so that's what we're talking about with interquartile range. Interquartile range is abbreviated IQR, and it's just Q3 minus Q1. Middle of the first half, middle of the second half tells us the width of the middle 50% of the data. Where do the typical values occur? All right, next I want to talk about standard deviation. Standard deviation is more about kind of from point to point. Okay, so the way we describe standard deviation is the average distance from the mean. Average distance from the mean. Well, mean is one of our centers, and so we're wanting to know is, on average, how far is each value from that center? So that's why standard deviation helps us give an idea of spread, because it tells us on average they vary this far from our typical. So were they a little better, a little worse, but you got your pluses and minuses there, because some are going to be higher, some are going to be lower, but you're getting an idea on average how much higher or on average how much lower. That's how you want to think through standard deviation. So we actually calculate it very similarly to how we calculate averages. Now, I'm going to show the formulation, then we're going to go to the calculator. Formula is nice to know because it gives us an idea of how that number is calculated. So later on we can figure out how to manipulate that number, like with sample sizes and things like that. But right now we want to focus on just how to calculate that. So the way we get standard deviation, first off, the formula is square root of x minus x bar squared over n. Well, why is it square root of x minus x bar squared over n? Well, x minus x bar, that's the distance from a value to the mean, correct? So value minus mean, take that, I left off my summation. So I'm going to do a value minus a mean. Now I'm going to square that because sometimes they're positive, sometimes they're negative. So the reason we're squaring is to kind of get those negatives out. Otherwise all of our stuff would cancel out. All the pluses over here and all the minuses over here, when you add them together, you get an average, they cancel out. So this means add all of those differences together and then divide by however many differences you had, how many terms you had. So it's the same average formula we talked about. I know there's a little bit of, doesn't follow real rules of averages because square roots of sums and things like that. But in general, that's the idea behind it. So that's our average distance. And then we square root just to undo all the squaring that we did. So that's kind of a nuts and bolts explanation of standard deviation. We'll go a little more in depth with that in class. Now you may be a little confused about this little symbol right here. This symbol is sigma. I just said this was sigma, right? That's capital sigma. You've seen that in the Greek letters. This little guy that looks kind of like a cursive O, that's lowercase sigma. Right? The Greek alphabet has capital letters and lowercase letters also. Sigma starts with S, S for standard deviation. So that's sigma for a population. So that's population standard deviation. STDEV. I'll often abbreviate standard deviation, STDEV. So sigma is just our symbol for population standard deviation. Just like mu was our symbol for population mean. So in statistics, we typically like Greek letters to represent what's going on with the population, and then we like American letters, American letters, English letters, those type of things for what's going on with a sample. Now in this one, it's not like mean. When you actually change the sample, you've really got to change the formula a little bit. So if we want to deal with sample standard deviation, and we just use SX for that, S sub X, that's going to be a very similar formula, sigma X minus X bar quantity squared, but now it's going to be over N minus 1. Why is it going to be over N minus 1? Because we use samples to estimate what's going on with the population. So by subtracting one from that denominator actually makes the value bigger, so it weakens the estimate a little bit. I believe it has to do with introducing what we call degrees of freedom, and we'll talk about those a lot more later. But the idea is we need to introduce the idea that there's uncertainty between a sample and a population. So we're going to introduce that uncertainty by just subtracting one. So by weakening the estimate just a little bit. So whenever you look at these, sigma standard deviations are going to be, for the same data set, are always going to be smaller than regular standard or sample standard deviation. Okay, so let's jump over to the calculator real quick and let's calculate what the standard deviation is supposed to be in this case, so we can use it for this problem. Back in the calculator, using one of our stats again, we can see up here towards the top, there was our mean. Here we see the SX and the sigma X that we just talked about. So SX is for a sample, sigma X is for a population, and so we're going to use the sigma X 10.94 as our standard deviation. So now, as we saw on the calculator, we got a standard deviation of 10.94. Remember, we had two different standard deviations, but we wanted the population standard deviation because this is all of Hank Aaron's home run seasons, not a sample of them. If he had played, say, 30 seasons and we had only looked at 23 of them, then we could use the SX off of the calculator, off the one bar stat. But since we are looking at all 23 seasons for all of the seasons he played, that's the entire population of his home runs. So that's why we're going to use sigma of X. So that's why we're using 10.94 home runs. So how do we interpret 10.94 home runs? Well, 10.9 home runs means that he typically varied from the mean by 11 home runs. So in any random season, he typically varied, his number of home runs for that season was typically 11 home runs off of the mean. So on average, he was 11 home runs from his overall mean number of home runs on any given season. Okay? So we just figured out how far all the seasons were from the mean, and we averaged all those together. Okay. Again, a little more specific than that, but that's the general idea. On average, he was 11 home runs off from his mean number of home runs for any given season. That one's going to keep taking us practice. That's one that still trips me up, as y'all can tell, as far as just trying to interpret what standard deviation means. So we're going to keep working that, because that one is a tough one. All right, one more measure of variability I want to talk about is variance. And variance is kind of an extension of standard deviation. Variance is variance is variance. It's just a measure of variability. That's all it is. Okay, so if it's really high, then there's a lot of variability. If it's really low, then there's a little bit of variability. But it's all relative to the data set. Okay, so variance, for what we need to work with, all we need to understand in this introductory course is that it's just our standard deviation squared. Okay? So when you get questions about variance, just think, oh, that's standard deviation squared. Okay? So it's really this formula without the square root symbol. That's what variance is. We'll talk later on in this course, but it's really more for another course of how we would use variance quite a bit. But again, for this course, introductory was variance is just standard deviation squared. So it's not on our calculator in our 1-var stats. So the way we calculate it is we just go grab sigma x, no matter which one it is. Okay, if it's a sample, we use Sx and we square it. If it's population, we use sigma x and we'll square it. And so we'll do our 10.94 squared. And then we throw that into the calculator, and you're going to get 119.68 home runs squared. So again, when you look at it with the units, what the heck are squared home runs? Again, it's a measure of variability. When it's really high, there's a lot of variability, meaning the person wasn't very consistent. And when it's really low, then there's low variability. It means that that group was very consistent. They didn't change a lot from one trial to the next. All right, so those are our measures of spread. We got range. We don't use it a whole lot in here. Our big focus is interquartile range, standard deviation, and then occasionally we'll talk variance. Now, how do we decide which one's appropriate? Which one should I use to best describe? Because I want one number that describes what's going on with this data set. So it again comes back to shape, symmetric and skewed. So in a symmetric distribution, something that's all nice and clean and we have tails are about the same on both sides, what do you guys think? Am I going to use interquartile range, or am I going to use standard deviation? Those are going to be the two focuses right there. Well, let's think about what we used in our distributions for center. When we had a symmetric distribution, we used the mean, right? So my mean is, so my mean is what's the best estimate of what's going on because it brings everybody in. Well, which of these two measures of spread kind of is using the mean? Well, if we look at it, that's our standard deviation. Because remember, standard deviation is average distance from the mean. The formula actually has each value subtract the mean. So if I want to use mean as my center in a symmetric, then I need to use the spread that uses mean as my spread. So my symmetric distribution is going to use standard deviation to describe its spread. And then that means that my skewed distributions would use interquartile range. Well, why is that? Well, if it's skewed again, if it's skewed, we're using median. We're really focusing on what's going on here in the middle. So I'm really ignoring those tails. If I want to know what's going on here in the middle of the data set, I don't care about this tail being a little fatter and this tail being a little skinnier or vice versa. So if I'm really just looking at the middle of the data set, well, what focuses on the middle of the data set? Interquartile range does, because it's the middle 50%. So what we should hopefully start to recognize is mean and standard deviation are married by definition, and median and interquartile range are married by definition. So that means when mean is appropriate, standard deviation is appropriate, symmetric distribution. When median is appropriate, then interquartile range is appropriate. That's for skewed distribution. Okay, now let's go over and let's talk about outliers, because that was kind of the next thing. We had shape, outlier, center, and spread. We've talked about how shape helps us dictate center and spread. Well, let's figure out what exactly makes an outlier. So before we can really talk outliers, I need to talk about 5-number summary, and I kind of mentioned that earlier before. 5-number summary and box plots. For us to be able to graph those things, we really we need to know all those pieces that we've just talked about. Now, this graph looks very different from the other graphs we've done, right? We've done histograms. They were a visual, they were a graph. We've done dot plots. Stem plot was a kind of graph. Well, box plot is the last kind of quantitative graph that we focus on in this course right here. You guys have worked on before, probably called them box and whisker plots. But in a box plot, we can see a lot of good things here. Now, the reason we're tying box plot to 5-number summary is because what we use to make a box plot. So in a box plot, we have what we call our maximum value. Check that. Our minimum value. Okay. We have our maximum value, and then we have the box. See, the maximum, minimum, they kind of make the whiskers out here. The box actually looks very similar to what we worked with right here with interquartile range, isn't it? Because remember how we just made that box in the middle of our graph? So when we're talking about a box for a box and whisker plots, it's really just talking about your quartiles. So this is your first quartile, this is your third quartile, and then that line in the middle of the two is your second quartile, which we already established was your median. So the reason we call this 5-number summary is because these 5 numbers summarize our distribution. They tell us where it starts, where it stops, and where its 25% breaks are, its quarter breaks. So a 5-number summary is nothing more than your minimum, your Q1, your median, your Q3, and your maximum. That's a 5-number summary. So I don't have to write out the names of those. If I say 5-number summary and then I see 5 numbers separated with commas, I already know what each one represents. I know the 4th one is Q3. I know the 2nd one is Q2. I know the 5th one is going to be the maximum. I know the 3rd one's going to be the median. Because you're saying 5-number summary, you're already telling me the positions of all of them without writing them. So that's how we want to write our 5-number summaries. All right, so that's what a 5-number summary is. We graph the 5-number summary with a box plot. So it's really straightforward to do a box plot. We need a box to describe the middle 50%, right? That'd be like your interquartile range. And then we need those whiskers to describe, all right, what's going on out in the tails of the graph. What's going on in the tails of the graph? How do we keep all that stuff ordered is with this guy right here. This is what a lot of people forget on. I want you to focus on making me a scaled number line. A scaled number line for you to line each of these 5 numbers over, for you to get those values lined up on, because that tells us where we have, where's our 25% really clustered, where's our 25% really spread out, are the tails really long, meaning that we have a few values spread over a long area, are the tails really, really close together, meaning we have a few values in a very tight area. Because remember, each one of these represents 25% of all of the numbers in the data set. So this scaled number line, that tells us what the spreads of each of those quarters of the data set look like. So we need a scaled number line, and then really straightforward, we just label. What do you think these over here represent, these little stars? Well, those little stars are the outliers. If you have it. Some people just put another couple of dots out there that are detached. I like a little asterisk or a star out there, so showing that we have an outlier. So what's this point right here? If the maximum's out here, not at the end of the whisker, because these are all the points on my data set, this value is actually your last acceptable maximum. Acceptable maximum. Well, how can we have values in our data set that are not acceptable? Well, if they're outliers, we might consider them unacceptable. Sometimes we might want outliers, treat them as acceptable, but maybe we're deciding that they're unacceptable. So we need to talk outliers now. An outlier, as we discussed the other day, it's not just a number that's far off from the others. That makes it an outlier because it's deviating from the pattern of the others. Because the others should be, because maybe all the other ones are clustered here, and then we've got an outlier sitting out here. Well, he's not clustered with all the other ones. That's what makes him an outlier. He deviates. So any values, and you can have multiple outliers that deviate from the overall pattern of the distribution. Any values that deviate from the overall pattern of the distribution. All right, so let's go ahead and graph our box plot here just like we had talked about, and then we'll come back and see if there are any outliers in there. So I'm going to give you a second. you guys graph the box plot on this number line right here. All right, so you should have got an answer. It looks like this. Okay, so in our graph, we can see minimum, maximum, Q1, Q2, Q3. Now, how do we decide if there are any outliers in here? Well, just kind of by looking at it, this doesn't look like there's probably an outlier here. Maybe this one, because this point seems way, way, way on out there. So maybe we need to cut off somewhere in here and treat that one as an outlier. So let's go ahead and calculate an outlier. An outlier is not like what you guys did in younger grades where you just look and say, well, that one's really different. We're going to make them an outlier. No, outliers have actual certain rules. There's a couple of different rules you can go with. Sometimes you'll see a 2 sigma rule. Is that value more than 2 standard deviations away, and so on. But what we're going to focus on is what we call the 1.5 IQR rule. All right, so what that says is we're going to create not the range of the distribution, but the acceptable range. So we're going to say, okay, let's get really, really generous, and let's take our distribution, and let's expand it out even further. And if somebody still doesn't fit in after we've expanded out 1.5 times, then they got to be an outlier. We're giving them a lot of grace by saying, okay, let's make everything 1.5 times bigger. And if you're still not in the distribution after we've done that, then you got to be an outlier. All right, so let's do the calculations and get the acceptable range. So that's what I think of for 1.5 IQR rule. This calculates the acceptable range, or acceptable interval of values. I don't really like to think range, because range is usually one number. This is actually an interval of numbers. All right, so how do we get that? 1.5 IQR sounds just like what it is. 1.5 times the interquartile range. And what we're going to expand is actually our box, our middle 50%. So to get our acceptable range, we're going to take Q1 and we're going to expand it to the left 1.5 times. So Q1 minus 1.5 IQR. And then we're going to take Q3 and we're going to expand it 1.5 times. Or we're going to take the box and expand it 1.5 times from Q3. So that's Q3 plus 1.5 IQR. And then we've got brackets there saying that if you would be inclusive on the ends of that. All right, so let's go through and do the math on this. We've already calculated. Q1 was 26. 1.5. Our IQR we already calculated. What was the IQR we came up with? It was 18 home runs. So we said that 18 home runs was the typical, spread for the middle number seasons. So 1.5 times 18. And then we're going to do the same thing with Q3. So Q3, which was 44, plus 1.5 times 18. So 1.5 times 18 is 27. So that tells us our left boundary is -1. 44 plus 27. Right boundary is 71. So this is our acceptable range. -1 to 71. So what we're saying is if we expanded our box all the way out here to -1, and we expanded this box all the way out here to say 71, if any values, so we just took that box and subtracted 27, that's 1.5 times 18. Took this edge of the box and added 27, that's 1.5 times 18. So if any seasons had home runs outside of -1 or 71, then they would be an outlier. Well, we can see that for Hank Aaron's season, his lowest was 10, so he didn't exceed that. So he's still inside that acceptable boundary. And then his highest was 47, so it didn't either. So he doesn't have any outliers on either side of that distribution. Now, say it had that 74 home run season that we had talked about earlier. That 74 home run actually would have been out here, right? So we would have then put an asterisk, and then the next number in would have been our acceptable maximum. So we would have stopped at like the 45 or whatever the number right before that was inside of 71 was. We'll look at some examples like that in class. But that's what we're talking about with outliers. You're going to take the left edge of your box and you're going to expand it 1.5 times the box. And you're going to take the right edge of the box and expand it 1.5 times. and that's creating a fence. Anybody that lies outside that fence, any values, then they've got to be outliers. They lie outside the acceptable range or interval of values. All right. That's one thing that we can get from box plot. The other thing is we can see shape. Just like with any type of graph, that's really the big reason we like graphs, is because they give us a good quick picture on shape. Now we said earlier that the shape on this distribution was skewed left. I feel like we see that pretty well over here, because 50% of our graph is bunched up right here in that 44 to 47 range, sorry, 34 to 47 range, and the other 50% is spread out from that 37 range all the way back to that 10. So we can see that the left side is a lot more spread out than the right side, so it tails off to the left. So when we have something that tails off to the left, then we can say that its shape is left skew. All right, well, by contrast on that, if it stretches out to the right side, then it is going to be a right skew distribution. And if it looks pretty much the same on the left and the right, so my right 50%, my lower 50%, and my upper 50%, if they're about the same distances and stuff, then we can say it's symmetric. So we can identify shape of a distribution off of a box plot as well. So this is how we kind of get numbers to summarize all that quantitative value. So taking a large data set and creating just a very few values that say, okay, this is what's typically going on in these different areas. So we can identify mean and median, right? Those are describing the typical value, the center. Mean is for symmetric distributions, median is for skewed distributions. We can describe the spread of the distributions using interquartile range and standard deviation. Interquartile range goes with median for skewed distributions, and a standard deviation goes with mean for symmetric distributions. And then we can calculate our outliers using 1.5 IQR rule. Span that box on the box plot by 1.5 times in both directions. And if you still can't fit into that really generous range we gave you, you're an outlier. We're going to denote you with an asterisk. So that's how we can use numerical summaries to analyze quantitative data. So kind of look back through this one a few times if you need to, because this is really, really important. These numbers are going to drive what we do kind of all throughout this course. And I will see you in class tomorrow, guys.